This is the June 2008 Regents Chemistry Solutions. We'll start with the multiple choice. Let's get going. So, it's moving on down to number 1. Let's zoom in here. And we're going to start with atomic structure questions. They tend to go in order. And let's do this. All right, number 1. In an atom in the ground state, has 7 valence electrons. This atom could be an atom of which element? All right, first and foremost, a couple of little vocab words. Ground state means electrons are filled from lower energy first. So here's a nucleus. Electrons are in shells that fill the nucleus first. There's 2 electrons in the first shell, and there's 8 and so forth. So we're not dealing with an excited state. They said the word atom, which means neutral, which protons equal the electrons always in an atom. And 7 valence electrons, these are 7 electrons outside of the filled energy level. So we're looking for 7 valence electrons. It's an atom in the ground state. Okay, so they had to say that it was an atom, not an ion. They had to say it filled in order. So now we're just looking for an atom with 7 valence electrons. So there is certainly a place we can look to find this. Let's go there. And here we are with the periodic table in your reference manual or booklet there. And let's zoom in, and we're going to look for valence electrons. And these are the electrons in the outermost shell. And if you look at group 17, there's 7 valence electrons. If I zoom in a little closer, you can see that if I've got 7 valence, okay, 2-7 or 2-8-7, these all are 1 electron away from being stable. So I think I'm looking for a halogen. Halogens are in this column: iodine, bromide, chlorine, and fluorine. Let's go back to the question. And there is my answer. Fluorine is 2-7, 2 electrons in the first row. Instead of having 8, it's got 7 electrons on the outermost shell. So number 1 is 2. Number 2. What is the total number of electrons in an atom of potassium? Now, some people think potassium is element P. If you forget, you have table S that tells you atomic number with element symbol and name. Potassium is not P, it's phosphorus, it's K. So by saying the word atom, it's telling me that protons equal electrons because we're neutral. So all I've got to know is how many protons potassium has. So let's look this up in our reference table, specifically the periodic table. So potassium, with 1 valence electron, likes to become +1, but what we're looking for is this number right here. This is the atomic number. This is the number of protons. This is what identifies potassium from every other element. Potassium is unique because it's got 19 protons. But this question said the word atom, which means it's electrically neutral. It does not have a charge. Okay, so that means the protons, which is 19, must equal electrons. We have a positive 19 in the nucleus, and therefore we can have 19 electrons, not going to draw all of them, that can surround it to make the atom. So this is 19 protons and also 19 electrons. Protons equal the electrons in an atom always because they're neutral. Now when it becomes +1, it does not gain a proton, because if it did, it would no longer be potassium. If you had 1 more proton than 19, you'd become the element calcium. Proton numbers identify the element. So when K goes to +1, and this charge tells you the charge it likes to become, so when this becomes the ion K +1, K still has 19 protons and +19 in the nucleus, but it has 1 less electron. It has 19 when it's an atom, but it loses a negative. Metals, like these are, lose electrons because they're held loosely to become positive. So 19. So potassium's atomic number 19, so it's got 19 protons, but also 19 electrons. Number 2 is 2. Hope number 1 and number 2 don't bother you because they're both 2 collectively. Shouldn't think that way. So number 2 is definitely 2. Number 3. A proton has a charge that's opposite the charge of a Well, I guess these questions kind of go in order. If you've been doing 1, 2, and 3, or 1 and 2 with me, a proton has a positive charge, positive proton. The electron is negatively charged, and they have the same size but opposite values. So a proton has the opposite charge of an electron, choice 3. Now, if you would like some place to help you think about this or give you some hints, table O can help you. Let's go there. Some teachers keep table O for the nuclear chemistry unit because you care about the nucleus changing, but I like to use table O for atomic structure for the particles as well. Okay, proton has a mass of 1 and a charge of +1. An electron, now it doesn't say this here, but a beta particle is an electron. It's got, they say, a mass of 0. Now, in truth, an electron is 2,000 times lighter than a hydrogen, or I should say, a proton, or a neutron, right? Neutron's also a mass of 1. So it's so tiny compared to these two that they give it a 0. But look carefully. It's got a charge of -1. A proton has a charge of +1. So they're equal but opposite. So an electron is opposite the charge of a proton. And of course, when you put these together, okay, one of each, you get a neutral charge. That's why atoms have equal protons and electrons. Number 3 is 3. Number 4. Which conclusion was a direct result of the gold foil experiment? Okay, gold foil experiment was done by Ernest Rutherford. And what he found by shooting alpha particles, which we now know are helium nuclei, by a very thin piece of metal, most of these alpha particles went right through. These are big particles. Occasionally some deflected, okay, and even some bounced somewhat back, which told us that the atom is mostly empty space, not a solid sphere. And because some bounced almost back, though, that nucleus had a very dense, positively charged nucleus. Now they knew that because the alpha particle they knew was positive, because when they shot it through an electrical field, they saw it deflect upward toward a negative field. So they knew it was positive, and when they saw it deflect away, they used the conclusion that the nucleus also had to be positive because like charges repel. So it looks like the first choice is the best. Mostly empty space because most of these alpha particles went right through. Because of the infrequent deflections, that's why it's mostly empty space, away from the center, it showed us that the nucleus was also, okay, positively charged. And all the mass of the atom, of course, in the nucleus. So, of course, number 1 is the choice for number 4. Number 5. Which statement identifies element arsenic? Okay, now arsenic is As. If you don't know, table T can help you. I meant table S. Sorry. So table S can help you. And as I've mentioned earlier, table S gives you a bunch of information: ionization energy, electronegativity, attraction for electrons, melting point, boiling point, density, and the size of the atom, okay, as long with the name and the symbol. So arsenic, if you didn't know arsenic was As, atomic number 33, here it is. Okay, and they give you some information here. Now, what makes arsenic special? Well, it does have some unique amounts of ionization energy, electronegativity, melting points, and density, but what makes all atoms special are their atomic numbers, the number of protons. So let's go to the periodic table and find how many protons arsenic has. So what makes arsenic special, just like germanium or gallium or any other element, is the number of protons, the social security number. Every person in our country has a unique one. Well, what makes it special is that unique number. Well, maybe. But what makes elements special and unique is a number of protons, and that's denoted by this atomic number. So arsenic is arsenic because of 33 protons. All the other numbers are important properties, But this is the overlying most important distinguishing characteristic of element arsenic, 33 protons. And if it's an atom, 33 electrons. So number 5 is 1. Arsenic has the atomic number 33, which means 33 protons. Okay? Now, if you look for the melting point, you say, Mr. Grotsky, wouldn't they have two answers there? If you look at the melting point of arsenic, is it 84? And is the radius 146? And does it have 8 valence electrons? These three choices actually do not match. Okay, arsenic. Case in point, 84 is the melting point, 146 the radius. Let's go to table, I get this right this time, table S. So arsenic, okay, right here, has a melting point of, well, not 24, 1090, it's a different number, and it has an atomic radius of 120. So these numbers do not match what was listed. In fact, if you didn't know arsenic was AS and you went too fast, you may think, oh, argon is arsenic, and you may have matched this number. 84 they list is for AS, arsenic. I'm sorry, for argon, okay? Yet, what they give you? They gave you 84 for argon when they were looking for arsenic. So they give you values that don't match up here anyway. Best answer by a long shot, number 1, number of protons 33. These values don't even match up with arsenic. Number 6. Which element has an atom with the greatest attraction for electrons? Okay, attraction for electrons, party people, okay, is another word for electronegativity. Get this word down, electronegativity. This is an important word, okay? It really spells out whether atoms have polar and nonpolar bonds, if the molecule can be polar, the type of tug on the electrons between a covalent bond, many different things we use this for. So who has the greatest attraction for electrons? Well, these usually are the atoms that are smaller because they pull in their electrons. So this is a property of nonmetals. As we go across the periodic table, the radii get smaller because the nuclear charge, the number of protons inside the nucleus, increases with the same shell. So the ones that pull in electrons more are the smaller ones, over to the right and up. So if you look at your choices, arsenic, bismuth, nitrogen, and phosphorus, they're all in the same group. Okay, so if you look, nitrogen, I'll just write it here, phosphorus, okay, then we have our arsenic, I think then we have a break, and then there's bismuth, okay, and I'm in the same group. I'm in group 15. And as we go down a group, okay, the radius gets increasingly larger. We become more like a metal. Now, why is that? Because as we go down a group, we're putting electrons in shells, we're filling shells up, but we need additional shells of electrons that are farther away. Or you could say the shielding effect, okay, that we use in this course is that as you add filled shells of electrons, now I'm using circles as a model, it's the Bohr model, it's not really circles, the current model of the atom is an electron cloud model, but I'm just using it based on proximity, positive nucleus. As you fill shells of electrons, okay, it's harder for the outermost electron to feel the positive pulling force because it has to get through these filled shells. So as you fill electron shells, they shield that negative from that positive, and these electrons can exist a little farther away. So metals are large, tend to lose electrons, the metallic properties increases. So of the 4, the greatest attraction, okay, would have to be the nitrogen, okay, just based on our periodic trends. Now, if you were following other questions with me, electronegativity is listed in reference table S. So if you weren't going to use your trends, if you didn't quite know this background information, which you should know because it's part of the Regents curriculum, as you go across the periodic table, it gets smaller because the number of protons increases. As you go down, the radius gets bigger because of more filled shells or that shielding effect. That's a trend you're responsible for understanding. But if you just wanted to figure it out based on who has the greatest attraction or the electronegativity, we could look it up. Let's do that. So table S, one of the most underutilized tables. Nitrogen is 3.0. Okay, scrolling down, we have phosphorus in the same group as 2.2. Then we have arsenic 2.2, and as we suspected, going all the way down to bismuth, okay, 1.9. So very clearly, as you go down, the attractions become less because the radii get bigger. You can see that along this way. But they were asking for the greatest attraction, so I'm going up with the smallest atoms, or the more electronegative atoms are smaller, and nitrogen is my answer. So number 6 is 3. Just be careful and read this, because if I was to go through this quickly, I'd probably put the read this incorrectly with the least attraction, but they want the greatest attraction. Just read it carefully. Number 6 is 3. Number 7. Number 7 is a question that comes up often in these review or these Regents that you take. It's one that comes up, seems like every other year. And you should know when you balance a chemical equation, you're certainly balancing or conserving mass. There are 2 hydrogens on this side, and there are 2 hydrogens on this side. There is 1 oxygen on this side, and there is 1 oxygen on this side. So the same number and same type of atoms are on both sides because we don't create nor do we destroy, okay, atoms. Now you may be fooled and think, well, energy is not conserved. Well, energy was given off because this had a lot of energy to begin with. Okay, things that are exothermic had a lot of energy to begin with. We didn't create nor destroy energy either, so energy is also conserved. And if you look carefully, this side is electrically neutral, right? A +1 and -1, and this side is electrically neutral. So we are balancing mass, charge, okay, and energy. So the best answer is number 4. We're always balancing energy. We're always balancing mass. The charge gets people because they think that only occurs in redox reactions. But no, mass, charge, and energy always conserved in a balanced chemical reaction. 7 is 4. Number 8. And number 8, which statement describes the composition of potassium chlorate? All right, potassium chlorate clearly is a compound. How do I know? It's got a chemical formula, which tells me there's an exact ratio of different type of atoms. So there's 1 potassium to 1 chlorine to 3 oxygens in this compound. And it's unique to other compounds because of its unique ratio of these different types of atoms. And you make it chemically and you break it down chemically because they're chemically bonded. So which of the 4 statements talks about this compound? Number 1, the proportion by mass of elements in potassium chlorate is fixed. I like that answer because the percent by mass of elements doesn't change. You may say, what do you mean by that? Well, if you take the entire mass of 1 mole, 3 times 16 plus 35.4 plus 40, 40, and we equal that out, we get that mass per 1 mole, the formula mass, whatever that might be, and I don't care what it is, it'd be this number, the formula mass. And then if I was to take the mass of just potassium, in this case it'd be 40, okay, over, actually, I'm sorry, 39 over this formula mass, we would times it by 100, we would come up with some percentage. And this percentage, whatever it might be, okay, would never change because there's only 1 potassium per the entire thing. So percent by mass is one way we're able to identify what compound we have because the percent by mass of compounds are fixed because the formulas are fixed. You're not going to see all of a sudden 2 potassiums here. If this is potassium chlorate, there's only 1 potassium per all of these. So that's why 1 is the best answer. Look at the choices. The proportion by mass of elements varies. Well, that would be for a mixture. Mixtures you can have dilute and concentrated amounts, but a compound has an exact number of stuff and type of stuff. Potassium chloride is composed of 4 elements. Well, count the capitals. There's only 3. And 4 potassium chloride is composed of 5 elements. Again, silly. There's not 5 different letters here. Okay, there's only 3 capitals, 3 different elements. Number 8 is 1. Number 9. As a bond between a hydrogen atom and a sulfur atom is formed, electrons are. Okay, let's evaluate what type of elements these are. Hydrogen and sulfur. Are these metals or nonmetals? Well, hydrogen, okay, is a nonmetal. And sulfur is a nonmetal. Let's go to the periodic table so we can understand how we can differentiate between metals and nonmetals. All right, so in this area we have our metals. I'm sorry, nonmetals. So in this area is our nonmetals. What's so special about nonmetals? They're the smaller atoms that attract electrons really well. Okay? And in this side of the periodic table, you've got your metals. They tend to be bigger, hold on to electrons loosely, and they lose them. They oxidize. Nonmetals tend to gain because they attract them. They have high electronegativity. These metals have a low attraction, low electronegativity. Now what separates them is the metalloids. These have properties of both. So this is the dividing line. Everything above to the left of the staircase is your nonmetals. Now, everything to the left is your metals. The exception is hydrogen. Hydrogen is really a nonmetal, but they put it over here because it has one valence electron. Okay, so that's something you had to know. And one way to figure that out is table S. If you look at its electronegativity values, they're so much higher than that of metals. I'm sorry, and metals, of course, have low attraction. This has a high attraction. So if you did a periodic table graphing activity or a lab, you'll see that the hydrogen is kind of the outcast here. All right, so hydrogen is a nonmetal. So if we were to put a bond between an H and an S, now S has 6 valence electrons. So it's probably going to bond, not probably, definitely going to bond to 2 H's. Each H brings an electron to the table, and now sulfur has its octet. Okay, and hydrogen feels happy because it's sharing 2. Now I'm saying sharing for a reason here. Covalent compounds, and these are compounds between nonmetals, have to be sharing electrons. Why? Well, nonmetals both have very relatively high attraction for electrons. That's why they're smaller. That's why they tend to attract electrons. So hydrogen has a pretty high electronegativity, and so does sulfur. So if you have 2 elements that are pretty strong, think of a person pulling on a rope with a baby. It's like me pulling a rope with my 3-year-old. We have a tug of war. Okay? Now who's going to win? Well, if it was my baby and I would pull the rope away from my baby because I'm so much stronger. And this is what would happen in an ionic bond. Metals hold on to electrons loosely, whereas nonmetals hold tightly. But in this scenario, we don't have a metal that holds on loosely. We have 2 strong people. So 2 strong people having a tug of war would be forced to share that rope, because both of them are strong for electrons. So you're not going to have one person yanking the rope away to create ions. So we share and form covalent bonds. Covalent bonds are between nonmetals. Nonmetals have high electronegativity, therefore they're forced to share. Now, if you have an ionic bond where you make, guess what, ions, then for instance, sodium has 1, chlorine has its 7. Okay, I'm going to draw that again because there's so many dots going on here. Okay, so we have sodium with its 1 and we have chlorine with its 7. What's going to happen, party people, is that chlorine is going to rip this electron away from the sodium. Sodium is going to lose its valence electron and become positively charged. Chlorine had 7, and now by the 1 it gained, now has 8. And the whole thing is negatively charged, and they attract by an ionic bond between them. Okay? By transferring, we make ions. By sharing, we make covalent bonds. Number 9 is 2. Number 10. Number 10 states atoms of which element can bond to each other to form chains, rings, and networks. Okay? Well, a network would be like a network solid that we used to have in this course, and that is what makes diamonds. Okay, if you take a tetrahedral diamond and continue that tetrahedral in all directions, you get a network solid. It's a crystal of covalent compounds. Notice I have carbon here. Rings, cyclocompounds. You might have learned about cyclopentane. Okay, that's a 5-sided, basically ring. Have to put in the H's, of course. Every carbon makes 2 bonds, but that's a cyclopentane. And of course, chains, okay, of electrons can also be made. Basically, what you're describing is a hydrocarbon chain of organic compounds, and we're dealing with carbon as the chemical that we make these chains or links with, okay? And one of the reasons it can make 4 bonds, because it's 2-4, it needs what? 4 more electrons to satisfy and make the 8 to make it stable. So hydrogen only needs 1 more bond. Oxygen needs 2. Fluorine needs 1. Carbon, okay, can make 4 bonds. And that's one of the reasons. So you should have been thinking organic chemistry. Number 10 is 1. Number 11 states which formula represents a polar molecule. Okay, now polar means you are making 2 different sides of a molecule having different charges. So you're going to have a side that's a little bit positive and a side that could be a little bit negative. The only way to do that is have an unequal distribution of electrons between the nuclei that are bonding. So what I mean by that is, in a molecule of 2 or more different atoms, you may have more electrons existing on this side of the molecule than this side, which gives it an overall negative feel on this side, and the side that has less, okay, negatives has a feeling of being more positive. That's truly how a polar molecule works. Now, interesting enough, they stick together because the more negative side attracts, okay, the positive side, okay, and the more polar you are, the more that electrons are shared unequally, okay, the larger these negatives and larger these positives, and therefore larger these attractive forces, which will make for a higher boiling point. Water has pretty strong attractive forces. A lot of implications here. Now, what creates a polar molecule? There are 2 basic parameters that do so. Number 1, to be a polar molecule, you have to have a polar bond. Okay? So you have to have a polar bond. Now, why do you have to have a polar bond to be a polar molecule? Because some people confuse the word polar and think it just means all the same thing. Well, a polar bond means that between 2 atoms, so if I've got atom A and atom B, and polar and nonpolar has to do with covalent compounds, okay, sharing electrons unequally. Now, if A has a larger electronegativity than B, and you should know electronegativity is attraction, the pair of electrons are held closer to A, and that creates an unequal distribution of electrons, and that's where that really comes from in the molecule to give the negative side and the positive side. So it all starts with having a polar bond. If your molecule, made of 2 or more different atoms, does not have any polar bonds, then it could never have a negative or positive side. Case in point, look at this guy right here. Br, this one has 7 valence electrons, and another Br, just change the color so you can see, has another 7 valence electrons. Don't know why I'm doing X's when the different colors work. So you can see that by sharing, both sides have that magical 8 number. So they're both stable, and that pair of electrons they're sharing is 1 bond. But more importantly, they're sharing these guys equally because they're the same element with the same electronegativity. So in order to be a polar bond and satisfy the first requirement for a polar molecule, you have to have 2 or more different atoms, okay, because the two more different atoms will have different electronegativity. So this is a nonpolar compound. This could never be polar. This could never create an unequal distribution of electrons. So one we cancel out. Now, the second requirement to be a polar molecule is you must have asymmetry. And I'll explain. If you are symmetrical, and really we need asymmetry, if you're symmetrical, meaning in this course the same in all sides, okay, in these two-dimensional drawings, that's as far as we'll go in this course, okay, then what happens is if you have a polar bond and you are symmetrical, what could happen is this unequal distribution of electrons you have across one bond will be the same throughout the entire molecule. And if you have the same unequalness in all directions, then there's no difference to the side. Case in point, here's methane. Methane has 4 polar bonds because there are 2 different nonmetals. Carbon has 1 valence electron, and hydrogen has the other. And everybody's happy. Carbon has its 8, hydrogen has its 2 that fills the first energy level, and there it is. But because it makes 4 polar bonds in all directions, it's equal in its unequalness, meaning there's no difference to one side of the other. So that's what's happening here. So these four polar bonds cancel themselves out because there's no difference to each side of the molecule because their unequal sharing is the same in all directions. Here we have clearly differences in different directions. Here they're all the same. So CH4, choice 3, is not an answer. It's got polar bonds. It satisfies the first postulate, but because of its symmetry, the same all the way around, okay, those 4 polar bonds cancel out. Now CO2 will draw next. Now CO2 is drawn like this, okay? Carbon has 4 valence. Oxygen has 6. We need a double bond to create the octet for the oxygen and a double bond to create the octet for the other oxygen and the carbon. Carbon is sharing a total of 8, okay, or has an 8 total by sharing. Now, this is a linear molecule because carbon doesn't have any lone pairs above. Let's get this out of the way. So because it stays linear, okay, because it stays linear, these 4 polar bonds collectively are equal on both sides. So this is symmetrical. That means that there's no difference on either side. This has the same unequal distribution as this side does, so therefore there's no difference to each side. So this is symmetrical, and CO2 is another non-polar molecule that has polar bonds. The first postulate was satisfied, but because of its symmetry, okay, it is a non-polar molecule. NH3 has to be the winner. Okay, now why? Well, if you draw NH3, Lewis dot diagram, lone pair, 2 lone pair. Here's its 5 valence. H comes by with 1 each, 1 valence electron. And look what you have here. You have the 8 with the N. Now, this is not the same all the way around. This is asymmetrical, and as the whole thing shakes here, looks like I had a mini earthquake. I didn't. Okay, but here's my 8 electrons for the N, and because of asymmetry, okay, and not the same all the way around, these polar bonds don't cancel, and we're going to have electron-rich area. Now, in truth, this lone pair actually repels the other ones down into the top of a 3-sided pyramid, and it gives a rich electron area on top and a poor electron area at the bottom. But all you have to know very clearly, it's not the same all the way around. So this has polar bonds, but, and satisfies 2 different nonmetals and satisfies the first postulate, and it's not symmetrical, so therefore it is asymmetrical, and it makes this a polar molecule because the polar bonds don't cancel. There's no equalness in all directions. There's definitely a difference on these sides of the molecule than this side. So number 4 is your answer. It's a polar molecule. It has polar bonds. It has asymmetry. Only choice that does. Number 12. Number 12 states, two solid samples. Each contains sulfur, oxygen, and sodium only. So these solid samples contain these 3 different elements. These samples have the same color, melting point, and density. So they're made of sulfur, oxygen, and sodium, and these 2 samples have the same physical properties, intensive physical properties. You can identify color. Melting point is an intensive physical property where you can identify something based on its melting point, and density. Not only that, it has a unique reaction with aqueous barium chloride. So we have physical and chemical properties that are the same for the 2 samples. It can only be concluded that these are not mixtures or solutions. See, a solution and a mixture, okay, will not have, chances are, the same density, melting point, or colors, okay? It's almost impossible to make 2 mixtures that are exactly the same, even with careful measuring. This is clearly going to be something called a substance, but the problem here is that we have sulfur and oxygen. These must be bonded together in a fixed ratio to make a compound. See, individual atoms lose, or elements lose, their individual properties to become a brand new substance when they bond to make a compound. So therefore, the only good answer is choice 1. They could not be an element, these 2 substances, because they're a group of elements. And if they were an element, they would all have unique, or they'd be retaining their individual properties, and it would be a mixture. So the only way this for not to be a mixture is that these guys were bonded in a particular way with a particular chemical formula. It could have been something like what? Sodium, okay, sulfate, okay, which would have this formula. And I don't know exactly what it was, but if it was bonding this chemical formula, they'd have to have the same exact chemical formula. Therefore, they would have the same exact physical properties and chemical properties. So the key was that they had the same physical and chemical properties, and therefore it had to be a compound, which by definition is a group of different, 2 or more different atoms chemically combined. So number 12 was 1. Number 13 states, which equation represents a physical change? Now, a physical change is a change where the chemical formula does not change, just the distance between them. So if we look at choice 2, hydrogen bonds to itself and O bonds to itself to make a different arrangement of atoms. This is a chemical change. And if you look at choice 3, H2 and I2 make HI, a different arrangement of atoms. Chemical change. And N2 and O2 make a different arrangement. These 3 are all chemical changes. Now, a chemical change means that usually bonds are broken and new bonds are formed. And I say usually because sometimes you may have elements that are not diatomic here, but normally bonds are broken and reforming a brand new element. I always say chemical changes make a new substance by pulling apart the atoms, the bonds, and reforming new ones. In the case listed above, you should know a phase change is a physical change because the chemical formula is not changing. We're not pulling apart atoms and recreating something new. Yes, we're creating a liquid who has more energy than a solid, but the particle that makes up the liquid is still the same. There's just a physical distance between them. In the case of water, we have these H2O particles in a crystal, and they have a lot of space between them, and when they become a liquid, these particles don't change. It becomes a little more dense and a little more disorganized, the entropy increase, but what's in the particle, H, 2 H's to 1 O, stays constant. So phase changes, evaporation, in this case melting, freezing, condensation, sublimation, a solid going to a gas, or deposition, a gas going to a solid, are all physical changes because we're not creating something new in terms of breaking bonds. We're just changing the physical differences, okay, that exists between them. So number 13 is 1. Number 14. Which liquid has the lowest vapor pressure at 65 degrees Celsius? Now, if you knew this answer, man, you're the geek of the century. Why would you know this? Well, maybe you know because you know of the 4 liquids, propanone evaporates faster because maybe your teacher swiped these liquids on the top of a desk and you saw that the propanone, which is really acetone, fancy name, prop for 3 carbons, one for the ketone, evaporates the easiest, had the weakest intermolecular forces of attraction. If you didn't know any of that, and that's okay if you weren't the geek of the century like some of us, okay, you can look somewhere, and let's go there. So here we are with table H, which lists the vapor pressure of 4 liquids. And here's your acetone, ethanol is your alcohol, water, ethanoic acid, aka vinegar. This dotted line represents the standard pressure pushing down on a liquid, which prevents it from boiling. Okay, now, vapor pressure, I tell my students, is really nothing more than a way to look at the rate of evaporation. If something is evaporating fast, I think of vapor pressure is the rate of evaporation. It's the pressure due to liquids. This is my container, and this is my line. Liquids, given enough energy, if they overcome their attractive forces for each other, will get to the surface and evaporate. And that force upward when they evaporate into the gas phase provides collisions and a pressure. Okay, so some liquids evaporate better than others. You can see that propanone has a steeper curve or steeper slope. So at 65 degrees, this is going by fives, I believe, 50, 55, 60, so 65, they just gave you one temperature. Which liquid, okay, has the greatest vapor pressure? Well, it's going to be propanone. Why? Because it has the steepest curve. So clearly propanone evaporates the fastest. Now if you wanted boiling points, boiling point is the temperature when the vapor pressure equals standard. So if you look carefully, propanone has a boiling point around 56 somewhere. Look at water. Wow, 100. Now water resists evaporation because you can see it's very flat line here. It takes a lot more energy to produce the same vapor pressure to oppose the atmospheric pressure. So that's why it has a higher boiling point. Okay, higher the boiling point, stronger the attractions. These guys have weaker. Any case, just a little extra there. Now, make sure I read carefully. They want the lowest vapor pressure. So they want to know who was resisting, okay, evaporation the most, and that would be my ethanoic acid. Okay, it was the one of the 4 liquids that had the lowest value at 65. So this would be this liquid right here, ethanoic acid. So ethanoic acid actually has stronger attractive forces than water. Propanone, of course, had the weakest attractive forces and had the highest vapor pressure. So the best answer is choice 1, the one that resisted. Okay. Number 15. Not 15 yet. Okay, so I couldn't help but bring this back up. So ethanoic acid has the lowest vapor pressure of the 4 liquids at this temperature. It resists evaporation the most. Number 15 now. Which substance cannot be broken down by a chemical reaction? Well, chemical reaction or chemical changes are breaking bonds. So if we're going to break bonds, we're going to make something new. Okay, that's a chemical change. But you have to have bonds to begin with. Now ammonia, you should know, is NH3. If you don't, here's a place we can go. Table L lists some common bases. All right, and there's ammonia, aqueous ammonia. Okay, now it's not an Arrhenius base, as we've talked about previously in other lectures, but it's a base and it's a compound. So if you need to know what ammonia was, NH3 is there, but you should know that one. Argon, from table S, is an element. Symbol is Ar. Methane you should know from your organic unit. Meth means 1 carbon. Ane means it's saturated, so the rest of these are H's. Okay, so it's a compound, 2 or more different elements. Hopefully you know what water is. It's a compound, 2 or more different elements. So if you look at your choices, party people, you have compound, compound, and a compound. The one that is different that you cannot be broken down into anything simpler because it's already made up of unique atoms differentiated by their different number of protons is argon. So 15 is 2. You can't break an element down into anything simpler, but you can break down compounds because compounds, like this one CH4, can be what? Broken down into individual nitrogen and hydrogen, in this case carbon and hydrogen and oxygen. All of these compounds can be broken down into their elements that make them, but you can't break down an element. So that's all that was. And if you didn't know argon was Ar, not a compound, you could check table S. Let's do that. And table S lists atomic number with the symbol with the name. So if you didn't know argon was Ar, there's a place to look, okay? Table S is your friend, okay? Number 16. Which sample is the average kinetic energy of the particles the greatest? Average kinetic energy is temperature. Let's get that right. Temperature. Temperature is not a measure of total energy. It's a measure of the average motion. Right. Your teacher might have drawn a Boltzmann distribution graph. This represents, okay, number of molecules, and these are different speeds or velocities. And most elements, or most particles, are near the average, some way above, some way below. If you increase the temperature, this curve flattens out more, and you have a greater range, but you see the average increases. Okay, so because it's an average, we could care less about the size of the sample. You could have an average of a class of 30 people have an 80-point average or GPA, and you can have an average, okay, of a, I don't know, 4-person class have an 81. And you might think, well, 81 has a total great amount of energy. No, it doesn't. It has the highest average, but not the total amount of points. Okay? So we're independent of the size of the sample. We could care less. So who has the highest temperature? And if I'm not mistaken, the highest temperature is choice 3. 16 is 3. Highest temperature, average kinetic energy is temperature. Number 17. Number 17, a thermometer is in a beaker of water. Whoa. Which statement best explains why the thermometer reading initially increases when LBR solid is dissolved in water? Well, if the temperature is increasing, that means to me that it's an exothermic reaction or process. Why do I know that? Well, if the environment is getting warmer, and the environment here is the water, it must be something in the water. Here's my water, here's my something, releasing heat into it. Who is responsible for making the environment warmer? Okay, and it's the LIBR, the chemical. So we say it must be because of an exothermic process. Now, if you don't trust me, let's go to a place so we can make sure that I'm right. Okay, so let's go to table I. Now, table I lists a bunch of reaction. It gives the enthalpies, or the heats of reaction. This is combustion reaction, organic fuels plus oxygen, CO2 and water. Look at the negative decreases in energy, so very exothermic. The middle part is synthesis reactions that show the energy changes when things are made. And the last half, okay, or last third I should say, are what I say, ionization reactions. And these reactions also show a delta H. Now, as I just erased, they tell you in the bottom of this table that if something is exothermic, there's a minus sign. Now, exo means heat is exiting. So if you look at lithium bromide, when it dissolves in water, it is negative delta H. What does that mean? That means my potential energy curve, I'm starting with a certain amount of LIBR, and then I'm ending up with Li plus and Br negative ions. That's the product, And the difference of where I start and where I finish went down -48. That's why it's negative. So how did it lose that energy? Because, well, it lost the energy to the environment, okay, to get stable. So the water has to get warmer. And you get this in your heads, exothermic reaction, heat exits the reaction. The heat is on the product side. Now let's get rid of some of this nonsense I have here, okay? If I look at the reaction, I would put the heat right here. Right here. Okay, heat is released, heat is exiting, and it goes into the environment, and the environment gets warmer. You burn fossil fuels in your home to heat the home. Okay, now if something was endothermic, that means the energy change went up. The products have higher energy than the reactants. How did that happen? They must be taking energy from the environment. So endothermic compounds make the environment colder because they take energy from them. Okay, so it's important you know the difference. All right. So the dissolving process is exothermic, choice 4. Now, entropy is chaos. Entropy increasing or decreasing is not going to change delta H. Okay, so that's a kind of an independent variable. They're linked, okay, through different equations, but we're talking specifically about change in temperature. We're talking about change in energy, and lithium bromide was responsible for the change in temperature because it released it. 17 is 4. Okay, which process increases the potential energy of particles of a sample? Hey, potential energy. Okay, people call this the stored energy. I call it the other energies that are not kinetic. But in any case, I know that potential energy goes up every time you take an energy. If I give my kids high sugar diet, the potential for them to, well, act out or use that extra energy increases. So if you give something energy, its potential to do something with it increases. So look at your choices here. Let's white out some things here so we can have some room. Yeah, the power, the white out. Yeah. Okay, now look at a heating and cooling curve. I'm gonna draw one. Now let's white that out because, okay, I'm not really good at that. So let's white this out. Good. Now let's make sure we're small enough. Here we go. So let's look at our phase changes. Now condensation, okay, is going to be where a gas becomes a liquid. Here's my gas and here's my liquid. And you should know that I'm going from a high energy gas to a lower energy liquid, so the energy is released. It's an exothermic reaction. Your curve is generally going down, so the potential energy is decreasing. Always follow the curve of your graph. High energy to low energy, how's that happen? Energy is released. So if you're losing energy, your potential to act out decreases. If my kids burn off their energy, okay, they sleep at night. They have a less potential to react. So condensation doesn't work. Solidification, well, if I continue this liquid line and now I'm freezing, so liquid becomes a solid when the kinetic energy stays constant. This was a gas going to a liquid here. Same idea, energy is released. Liquid to solid is also exothermic. How do I know? Liquids have higher energy than a solid, so energy had to be released. You lose your energy, the potential to act out decreases. So solidification doesn't work. Now vaporization, okay, is my winner because I, in this case, am going from a liquid, I'm going this way to a gas. Now if I draw it this way, a liquid going to a gas, so this is my liquid here, and this is my gas. To become a higher energy phase, I have to absorb energy to climb this energy hill. So I'm taking energy in. If I'm taking energy in, my potential has to increase. Now deposition, okay, that's a phase change where you go from a gas directly into a solid. And there's no liquid phase. So a gas directly to a solid. And if you notice, high energy to low energy, well, potential energy has to drop because you're losing energy. The only one that showed a climb of energy, that needed energy, that was endothermic, that took energy from the environment, gained energy, would have its potential increase because you're taking in energy, is vaporization choice 4. Number 18 is 4. Number 19, which sample at STP has the same number of molecules as 5 liters of N2 at STP? This is Avogadro's hypothesis. I call this the same problem. Same volume, same conditions of temperature and pressure, same number of particles. Avogadro called those particles molecules. So if this is a 5-liter container of one gas, guess what? Because of the temperature and pressure are constant, there's a fixed number of seats in a theater or a fixed number of positions a gas can occupy. There's going to be the same number of gas particles that would fit in this container at the same temperature and problem. So 5 liters of N2 would give you 5 liters of another gas. Okay, that's all that is. Same volume, same temperature and pressure, same number of molecules. They're not going to be the same atoms because we notice in one particle there's 3, 1 N and 2 O's, and one of these particles there's 4 H's and 1 carbon. So it's not going to be the same mass, not going to be the same atoms, it's going to be the same volume, same number of molecules, Avogadro's hypothesis. And to continue with this a little further, you know that 1 mole of any gas, if you took a good chemistry class, is 22.4 liters. Of which gas? Of any gas. So if you have the same volume, this is at STP, you have the same number of stuff. Well, that's what this is alluding to. Number 19 is 2, the same problem. Same volume, same temperature, pressure, same number of molecules. Number 20. Number 20 states, under which conditions of temperature and pressure does an oxygen gas behave least like an ideal gas? Okay, well, an ideal gas is like an ideal student. An ideal student has no attractions because it's no attractions with the students around him. You might have People magazine's most gorgeous person sitting next to you, but that person's not going to notice because he's so focused on a teacher. So an ideal student has no attractions. A real student, okay, is not so focused on his teacher. So he has attractions for the people around him. He's a little more social. He's not focused on a teacher. He's missing out what I'm saying. He might be talking right now. Okay? So I call this a hand problem. So if I want to make and behave least like an ideal gas, what I'm really saying, how can I make an ideal gas behave more like a real gas? Now an ideal gas is independent particles. They're random. Speak to an ideal student. Sometimes they'll like, how you doing today, John? I like turtles. It's a little bit random. Why? Because they're so focused on a teacher. They're independent people. They care so much about the teachers. They're so random. Well, ideal gases are so random. They have no attractions for the other molecules. They're totally random and they follow the gas laws perfectly. But I want to make this real. I want to make them really have attractions, which means we got to push them closer together. Okay, and they push them together, hey, okay, maybe they'll start noticing. Who knows? When you push them together, they're going to start attracting. So what factors will do that? Okay, well, I'll tell you what, the pressure has to increase because if the pressure on these molecules increases, you push them together. And the temperature has to decrease because I want to slow them down so that they start attracting each other. If you take a gas and you increase its pressure and decrease its motion, temperature is motion, average kinetic energy, they will become a liquid eventually. So the pressure, okay, is going to be high and the temperature is low. And that's how you do that problem. Ideal gas ideally have no attractions and no volume. Real gases really have attraction, really have volume. Number 20 is 2.
1. How is a chemical reaction affected by the addition of a catalyst? All right, well, when I hear about chemical reaction and catalyst and how it's affected, I think potential energy curves. Yes. And I know that a catalyst, okay, changes the pathway, creates an alternate pathway. It doesn't change where I start and where I finish. It changes, okay, that pathway. And to ride the slide, to get to the top of the hill, we call that the activation energy. Where you start to the top of the hill. If you want to ride a slide, you got to get to the top of the slide. So if a reaction is to occur, it's got to get to this highest energy peak. What a catalyst does is lowers that peak so that the activation energy, which was once this amount, is now lowered. And for the same amount of energy, we can now get more molecules to react. So the rate of reaction increases because the activation energy decreases. 21 is 1. You should know a catalyst does not affect the difference to where you start and where you finish in these potential energy curves. And we call that value delta H. And of course, what I just drew here was an exothermic reaction. 21 is 1, a catalyst. And this comes up in part 2s in so many different ways. Lowers the activation energy. Creates an alternative pathway that's overall lower in energy. 22. Number 22 states, systems in nature tend to undergo changes toward. All right, well, the one thing you should know is, generally speaking, things that are high in energy tend to want to become lower in energy. So things in nature tend to decrease toward or move toward lower energy. A rock on top of the hill eventually goes to the bottom. Things tend to go from the top of the mountain down the mountain. Waterfalls flow downward from high potential energy to lower. So it should make sense that we move toward lower energy, but that's not the only driving force. The other driving force, and this really is more understood with a better feel for thermodynamics and the laws in a higher chemistry class, but entropy, which is disorder, okay? Things in nature tend to go from big rocks into smaller rocks. The sand on the beach came from rocks, so things in nature tend to break down. Think of human life trying to go against entropy. Eventually we lose and we actually become part of the earth again, as morbid as that sounds. So systems in nature tend to undergo changes toward lower energy and more disorder, okay? So we tend to go to breaking down into smaller pieces, and that, again, that's just how nature works. It's kind of like your room. Your room at home doesn't naturally tend toward making it orderly. You don't sit back and think, wow, I got to mess up my room today because it just, nature keeps cleaning it up. No, nature keeps disorganizing. We tend to make our rooms, without even trying, a mess. So we try to fight it by putting what? Things back in their place, but eventually they become disorganized again. So understand, we tend toward, okay, lower energy, as things with high energy are unstable, don't stay in that position, and more disorder. Number 22 is 2. Number 23. What can be concluded if an ion of an element, now that's key to me, that means I'm charged, I'm positive or negative because I lost or gained electrons. I'm an ion. My protons and electrons don't equal the same thing. Okay, is smaller than the atom of the same element. All right, so let's think about this for a second. I'm going to draw a little drawing. Okay, let's white out some things that we don't need here. Now, for me, when I read this, I tend to make a visual so that I can understand. They said an ion of an element is smaller, okay, is smaller, so let's put the ion here, I-O-N, is smaller than the atom. So what happens when the atom, which was neutral, protons equal electrons, become an ion, it got smaller. Now for me, one way to memorize or think about this, the only reason why an ion would be smaller, if the nucleus can overcome the electrons which are on the outside of the atom and pull them in. Well, why can it all of a sudden do that? Well, if you take some electrons away, if the atom was to lose some electrons, then the protons outnumber the electrons that are remaining and pull them in. So this must be a positive ion, okay? Because I lost electrons and the remaining protons pull in. Now I also can remember that if I lose weight, I get smaller. So it's another way to remember this. Losing electrons makes you smaller. Lose electrons, you become positive. Kind of like redox. You think about, so aluminum, 0 becomes aluminum plus 3, it oxidizes. It loses electrons, and aluminum plus 3 is going to be smaller than the atom. Okay, so many ways to think about this. The ion is negatively charged. No, it's going to become positive because losing something makes you smaller. So the ion is not negatively charged. In fact, negatively charged particles or ions are bigger than their atoms. Like if you gain electrons, like F, when it gains an electron, becomes F negative. It has one more electron, and if now the electrons outnumber the protons and they pull away, you get bigger. And gaining electrons, gaining weight, you get bigger. Another way to remember it anyway. So the ion is positively charged because it has fewer electrons than the atom. Yeah, which means you lost electrons. And losing electrons, like oxidation, remember Leo, you become positive. Your charge goes up. And the other choice, ion is positively charged because it has more electrons than the atom. If that's the case, it'd become negatively charged and it'd be bigger. So 23 is 3. Number 24. Number 24 states which class of organic compounds have molecules that contain nitrogen atoms. All right, so I'm looking for types of organic compounds that have nitrogen atoms. Well, table R is your friend here, so let's go there. And wow, there is table R. And we're looking for nitrogen type of compounds, and I scroll down, and I don't see them yet, but they're going to be here shortly. And there's amines, and there's amides, both that have nitrogen attached to usually some carbon or organic molecule. Don't forget that this R usually means the rest of an organic molecule. An organic molecule normally is a hydrocarbon chain. Hydro meaning hydrogen and carbon. So amine and amides, although they're slightly different, and here's the general formula, okay, are nitrogens attached to a carbon chain. And choice 2 is the amine. Okay, alcohols, ethers, and ketones have carbon, hydrogen, and oxygen in their compounds, but no nitrogen. 24 is 2. Number 25. Which two compounds have the same molecular formula but different chemical and physical properties? Well, you should have learned that structure is king. What does that mean? You change the structure, you change the physical and chemical properties. That's why organic chemistry, the naming system, is based on the structure, not how many carbons and hydrogens, okay, as it is in organic chemistry. You know the structure, you know it has its individual properties. So we want the same molecular formula, but different chemical and physical properties. So we want the same molecular formula, but different what? Different structure, right? Different physical properties, different structure. What we're looking for is isomers. Iso means same. So same chemical formula, different structure. Now these are structural formulas. They're showing the bonding. So one is not the answer because one has chlorine, one has bromine. So clearly they do not have the same molecular formula. Okay, now look at 2. I got 1, 2, 3 carbons, 1, 2, 3 carbons. And if I count my H's, I have 3 plus 1 is 4, 4 plus 2 is 6. So the first one is C3, H6. The other one here is C3, but there's H8. And that's not going to work. They have different numbers of H's. So that's not going to work. So choice 1 and 2, I can cross off. All right, choice 3, I have 1, 2 carbons, so C2 for this one. This one is C3. I don't have to finish the problem out. These have different number of carbons. So by process of elimination, choice 4, okay, must be the answer. Let's just check. This is C2, and this is 3 plus 2 is 5 plus 1 is H6. O. And this is C2, H6O. These both have the same molecular formula, but different structure. This is an ether, and this is an alcohol. They will have different properties, even though they have the same number of carbons, hydrogens, and oxygens. Okay, 25 is 4. Number 26. Number 26 states which, or asks, which half reaction equation represents the reduction of a potassium ion. So I'm starting with a potassium ion, which means I'm charged. Look at choice 4. I'm starting with a potassium atom, which is neutral, has no charge. That can't be an answer. Number 2, I'm starting with another potassium atom. So it's either between 1 and 3. Now, what is reduction? You should learn Leo the lion says grr. Losing electrons, Leo, is oxidation. Leo the lion says grr. Gaining electrons is reduction. Now, how can I gain something get reduced? Well, what you're gaining is something that is negative, which makes your charge go down. So if you're gaining something, the electron should be in the reactant side of the reaction. The reactants react to make products. So this is gaining electrons. If you're gaining heat, remember, think of an endothermic reaction where the energy, right, is in the reactant side. Why? Because you need it to react. You're gaining or absorbing energy. That's why it's endothermic. So endothermic and reduction are very similar. Electron has to be on the reactant side, but be careful. Just because it's there doesn't mean it's right. We have to make sure mass and charge is conserved. Here's a positive one. Here's a negative one. The total reactant side should be 0, as should be the product side, and it's true. This is K0, it's standalone. So the charge works, the mass works. Number 1 is the answer. Okay, reduction is the gaining of electrons. Now, K plus becoming 0, okay, well, this doesn't make any sense because a -1 and a 0 is a -1 on this side and a 0, so this charge isn't even balanced. Okay, so any case, K plus, if it gives off an electron, okay, this wouldn't even work, but this is trying to show oxidation. Okay, in fact, if it was correct, this K would have to be K plus 1, wouldn't it, if you think about the charge? Okay, or plus 2, I'm sorry. If K plus was to lose an electron, this would become K plus 2. All right, but that would be oxidation. And by the way, if you look on the periodic table, K can only become plus 1. So for many reasons, this is not the answer. 26 is 1. Number 27. According to the Arrhenius theory, that's the easiest definition. The easiest acid base. What do acids do? Acids give off H pluses. What do hydroxides do? They produce OH minuses. So if it's the Arrhenius acid, and don't get your feathers in a flutter here, Arrhenius is the easiest definition. Somehow they produce H pluses. So it changes litmus from red to blue. We're going to need table M to see if that's right. And these are phenolphthalein. Need table M as well. Produces hydroxide ions is the only positive ion. Hydronium ions, which by the way is H3O plus. If you forgot where the hydronium ion is, let's go to table E. So there's my hydronium ion, H3O plus. Okay, now my friends in chemistry, Arrhenius stated to be an Arrhenius acid, the only thing positive in solution is an H plus. It was very, very simple. To believe an H3O plus exists would mean that somehow the water accepted a proton. And accepting a proton is that other definition. So water would act as a base, and you would make an H3O plus. So an H3O plus would be made if water accepts a proton. And that's the other Bronston-Lowry definition. They don't name it by name, but by accepting and donating a proton. So the H3O plus really separates the idea that the other definition is accepting and donating H pluses, whereas Arrhenius is very simple. H plus was in solution by the acids. So 3 can't be the answer, okay, or at least it shouldn't be the answer, okay, as the only thing positive. It should be H plus. Okay, let's continue on. Hydroxide ions is the only negative. This would be for an Arrhenius base definition. To be a base, you produce hydroxide. So this clearly isn't the answer. Let's go to the indicators. So we want litmus from red to blue. Let's see, litmus. If it was an acid, it would go from not red to blue. That would mean that we're getting more basic, so that can't be the answer. So we'll cross out 1. 2 changes phenolphthalein from colorless to pink. Well, if phenolphthalein goes from colorless to pink, that means our pH is also rising more basic, so that doesn't make any sense. I'm talking about an acid. So we're going to cross out 2. So we look like we're left with no real good answers. It can't, see, it really can't be a hydroxide ion here. Can't be. Can't be a hydroxide ion. That is definitely a base. It can't be 1 and 2 because these are making basic, the indicators are showing that a base is being added, or it's a basic solution. So the best answer is 3. Called the state on this a couple of years back. We had the test, and I never got a real good answer for this. Other than looking at the best choice, okay, anyone who teaches this for a long time, we say that Arrhenius believed that H plus was only thing positive. But in this case, okay, the best answer, it would have to be 3. So this, if it bothered you, good for you, because there they really are stretching the definition of Arrhenius here, because if you believe the only thing positive is hydronium, then you really are considering the fact that water is accepting an H plus. And that must mean you're talking about the donating and accepting of protons. So this is not the best way to describe Arrhenius. However, the other 2 choices are so poor, this is the only thing that we can go with. So 27 is definitely 3. It's the only answer that makes somewhat some sense. Don't like it, but it's one of those scenarios where the other choices are clearly so much more incorrect. Number 27, unfortunately, 3 is the best answer. Not liking the question. Number 28. Number 28 states, which type of reaction occurs when a high energy particle collides with the nucleus of an atom, converting that atom into an atom of a different element? You should know where you are in the test, okay? 1 through 30 of this test usually goes in order of atomic structure, periodic table, bonding, okay, physical matter behavior, okay? We're at the end of 1 through 30, so we're in the last unit, which is nuclear chemistry. But when you collide with a nucleus and you make a different element by changing that nucleus by a collision, we call that word transmutation. We're mutating the nucleus because it's changing its proton through a nuclear reaction. The nucleus is changing. What they're really describing is artificial transmutation, where you have one particle colliding with another nucleus to give a brand new nucleus. And this is artificial because you need to slam these guys together. Usually a particle accelerator can do that, or some other type of reaction setup that's not natural. So 4 is the transmutation. Describes how nucleus change. Example of artificial transmutation where we have a nitrogen nucleus and a alpha particle as listed in table O, and when it collides unnaturally in the sense that these don't normally occur in nature, you're going to produce a brand new nuclide or atom, okay, oxygen 17, an isotope of regular oxygen, okay, and a proton. So this is a type of transmutation where the nucleus or nuclei are changing from one element to the other because their proton number is changing. But notice that the mass number, 14 plus 4, 18 on one side is 18 on the other, and the charge number or the proton number, 7 plus 2 is 9 on the bottom, and 8 plus 1 is 9. Natural transmutation is when you have just one reactant naturally becoming more stable by emitting a particle. In this case, it's a beta particle as listed in table O, and making a nitrogen atom. Okay, and again, you can see the same numbers. 7 plus a negative 1 gives you 6, and 14 plus 0 gives you 14. So this is an example of another type of transmutation which you're responsible for knowing, and this is natural. And of course, the beta particle results, which is called a high-speed electron, okay, from a neutron splitting into a proton and electrons, why the proton number increases. Okay, so in any case, transmutation is the word we use for when the nucleus changes to become more stable by either natural transmutation or the example I previously showed you where you had two elements and that's artificial when they have to slam together. So number 28 is 4. Number 29, which particle is emitted when an atom of krypton 85 spontaneously decays. Now, spontaneously decays mean it naturally undergoes some kind of natural transmutation. We want to find what particle, okay, it emits to become more stable. So we have to go to table N, and that's our friend here. So let's go there. So here we are with table N, and here's krypton 85. Here's its half-life. Here's its decay mode, which is a Greek B sign with a negative. Now this is a beta particle. Okay, it looks a lot like a positron. This would be an alpha particle. So we've got this symbol. Now if you didn't know what this symbol meant, table O is your friend. And wow, there's table O. And a beta particle is what we're looking for here. And that's this symbol right here. That B positive here is the positron, and your alpha symbol is your alpha particle, and so forth and so on. The gamma radiation is that gamma symbol. Notice no mass and no charge. Any case, so it's a beta particle. So number 29 was just a question that really tests your ability to know that you have some information to look up, okay, on table N in regards to the type of particle emitted by the nucleus. Again, know where you are in the test. The first 1 through 30 questions go in order of atomic structure all the way through nuclear chemistry. So we're in the last part of the 30s. So the last couple of questions, a few questions here, have been nuclear. In any case, 29 is 2. Number 30. Number 30 states, what is a problem commonly associated with nuclear power facilities? Well, nuclear power facilities use something called nuclear fission. You should be aware of nuclear fission is splitting a nucleus with a slow-moving neutron, usually uranium or plutonium. It captures it and then it splits it into smaller fragments and some more neutrons that can go find other uraniums or other fissionable material. So it's the splitting of the atom. Now the problem is that these particles that are split sometimes are most often enough themselves radioactive, or a lot of times there's some unfissionable fuel that's part of the fission reaction. In any case, what we have with nuclear fission, unfortunately, is radioactive wastes that tend to have very long half-lives. So the problem with nuclear fission, especially nuclear power facilities or nuclear reactors, is that we produce waste that have to be stored locally. We used to ship these in containers and put them into some mountainside somewhere, but we realized that's not going to work because, well, the containers eventually leak, okay, and they can spill, and the movement of these wastes, okay, in our public roadways is also very dangerous to have as well. So right now, nuclear facilities have to store the wastes on site. Now, let's go through the questions. So 30 is definitely going to be 4 here. The other questions are not correct in the sense that a small quantity of energy is produced. No, fission, okay, or any nuclear reaction produces tremendous amount of energy for the fuel it uses. Of course, fusion, okay, the fusing of atoms together produces more energy than fission, but collectively, all nuclear reactions produce a lot of energy, okay, more so than reactions with electrons. So 1 is crossed off. 2, reaction products contribute to acid rain. No, one of the positives of fission is that we don't have any really byproducts of what we would have if we were burning fossil fuels. Burning fossil fuels tends to have sulfur associated with, and with some heat and oxygen you make SO2s, and SO2s eventually with water make H2SO3, which is sulfurous acid, or H2SO4, which is sulfuric acid. So these are acid rains or byproducts of burning fossil fuels. When you use nuclear power, you don't have these uh, side reactions that we get. So that's a positive, all right? So that's crossed off. And it's impossible to control nuclear fission. Well, if that's the case, every nuclear power facility would be essentially a bomb, and one that would just spew radiation because it would have meltdowns all over the place. Yes, we can control it. Okay, so it's controlled fission. So of course 30 is choice 4. Number 31. Okay, now we're starting part B2. These are the multiple choice questions that are essentially two-step or higher thinking questions, a little more difficult. And again, they start in order of atomic structure, periodic table, through bonding, and eventually nuclear chemistry again. So knowing where you are in the test can be very helpful. And here we are starting again with our atomic structure question. The wave mechanical model of an atom is required to explain. Now, the wave mechanical model is the current model, sometimes called the electron cloud model. It is essentially based on the fact that electrons do not exist in orbits like Bohr said. They exist in something called orbitals, which is a three-dimensional space around the nucleus. Where the electron exactly is based on probability, but we can say with high probability electrons are in a certain area called an orbital, and a pair exists in an orbital. Now we use the word orbital to give a lot of credit to the orbits that Bohr made in his earlier model. And the reason why we give credit to Bohr is because he was the first to quantize the atom. He said electrons exist in specific energy levels based on their orbits and their proximity to the nucleus. Well, he was wrong that they exist in orbits, but he was right that electrons existed with distinct energy levels based on proximity to the nucleus, except they weren't orbits, they were actually these shells or these orbitals that existed. So to go from one to the other was still an exact amount of energy. So a lot of what he did was correct. It's just that his electrons didn't go in orbits, they stayed in these areas. In fact, his first orbit was matched by the outermost ring or outermost probability for electrons exist. So you can see why he would come up with that. Any case, something else about the wave mechanical model, electrons exist as waves and as particles. It's called a wave-particle duality. So when you're talking about the modern model, we're talking about electrons having wave properties, okay, as opposed to just straight negatively charged tiny particles. Also, we're using the word probability, another word, because we cannot narrow down exactly where one electron is. We can just say with a probability where it can be mostly be found. So wave properties, probability, and the word orbital are all your key words for this type of system. Let's go back to the question, okay? So the wave mechanical model atom is required to explain the mass number and the atomic number. No, those are earlier work. Moseley and his X-rays, okay, K lines was done there. Organization of atoms in a crystal. No, that was more done with shooting X-rays through crystals, X-ray crystallography, like how we came up with the structure of DNA. Radioactive nature of some atoms. Well, I do not think so. That is really the way to go here. Radioactive nature of some atoms based on really the nucleus stability, not so much the electrons, not at all the electrons. So the best answer is choice 4, the spectra of elements with multi-electron atoms. Now you say, well, how in the world is that the answer? Well, the Bohr model, as I just talked about, okay, was one where Bohr successfully explained the different energies emitted by a hydrogen atom. But what he couldn't explain was any other atom besides hydrogen. So his model kind of fell apart. So wave mechanical model or quantum mechanics was able to somewhat try to explain why multi-electron atoms, remember hydrogen only has one, gave off the different types of spectral lines. So the only way to explain anything beyond hydrogen, we needed a better model than the Bohr model, and the wave mechanical model is what did that. For instance, the wave mechanical model did its best to try to explain why there was very bright lines and very, very thin lines, okay, because of the interference patterns that electrons had with themselves when they're waves. Remember, if you have two waves hitting, okay, you're going to get interference patterns, okay, and you're going to get also you're going to get constructive interference and make bright lines and negative lines. Any case, that's really too much detail, but you should be aware that the Bohr model fell apart after hydrogen because he wasn't able to explain the other spectral lines, which is the energy levels when electrons jump back, and the current model was able to do so. So number 31 is 4. Number 32. Magnesium and calcium have similar chemical properties because an atom of each element has the same total number of what? Well, the periodic table, notice, is going in order, 32, and now we're in periodic table question. Magnesium and calcium, okay, are very similar. They're under each other in column 2 of the periodic table, and beryllium's on top of them. And the reason why they're in the same column is because they have the same number of valence electrons. Now, certainly Dmitri Mendeleev did not know about valence electrons at the time, but he did notice when he was putting his periodic table together, as did other people who were doing the same work, he was the first to publish, okay, that they had similar chemical properties. And it came later that they had the same available electrons available for bonding. Let's go to the periodic table to see that. Okay, so group 2, the periodic table. Here we are with beryllium, magnesium, and calcium as promised. I delivered. And if you notice, they both have 2 electrons. Remember, 2-2 means 2 electrons in the first energy level, and then 2 in the outermost, in this case, the second. 4 electrons total because protons equal electrons if they're atoms. Notice magnesium, and let's make this up close and personal for magnesium, is 2-8-2. And you notice it has 2 valence electrons on the outermost edge of its arrangement. And of course, calcium also has that outermost 2. So they all love to lose 2. That's why they all become +2. So all of these atoms were put under each other, not because they knew the electron arrangement or valence electrons or anything like that, because he just noticed that when you put atoms together in their order, and he was using atomic mass at the time, but now we use atomic number. When he's putting these atoms together, he noticed that the properties were periodically repeating themselves because we were filling the shells of electrons. Periodically, we'd start filling and then we get filled. And that's how it works. And when we were filled, okay, in the most simplistic case, we had these noble gases, helium, neon, okay? Now argon, krypton, and xenon, these guys don't have filled energy levels. They have that octet number. They have that special 8 on their outermost edge that makes them stable. Now, helium and neon are the electrons with filled principal energy levels. 2 electrons fills the first. Helium, of course, has 2. And 8 fills the second. Okay, so you should know that argon, krypton, and xenon do not have filled principal energy levels, but are stable nonetheless because they have that 8 on the outermost. So with those that took a more advanced chemistry class and now taking their regents, there's something special about filling your s and p orbitals. Okay. So this is a core concept you really have to know. Same or similar chemical properties, you're in the same column because the same number of valence electrons, same type of bonding. All right. Number 32 is 2. Number 33. Number 33 says the diagram below represents a nucleus of an atom. The question states, what are the atomic number and the mass number? Okay, well, I know that these are the protons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 protons, and I should know the atomic number. Okay, the number that identifies the element is the proton number. So I've got an element with 9 protons. So I'm going to write that on the bottom here. Now, who has 9 protons? Well, it would be an element, okay, that we can look up. Why not for fun? And number 9 is fluorine. So we're really dealing with fluorine here. Let's go back to the problem though. Okay, how many neutrons? Because they want the atomic number, which we have is 9, and they want the mass number. Now, the mass number of a nucleus, as Ernest Rutherford found, that the entire mass of the atom is due to the very dense nucleus, and most of the atom is empty space. In the nucleus, you have your protons and neutrons. So let's count the neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I've got 11 neutrons. Now, what's the mass number? Well, the mass of the entire atom is due to the protons and neutrons. So I'm going to add them together, and 9 plus 11, okay, add these together, gives me 20. So my mass number is 20. Now you may say, Mr. Gratzky, how do you know that neutrons and protons have the same mass? If you forgot that, table O is your friend. Let's go there. So you should know that neutrons' top number is the mass number, has a mass of 1, and a proton has a top number of mass of 1. Notice the neutron has no charge. The bottom number is the charge number. Hydrogen has a +1 charge. And notice electrons, by the way, you should know this is to be an electron. A beta particle is an example of a high-speed electron, but electron has a mass of 0, which is not really 0. It's 2,000 times lighter than that of a proton or neutron. But we consider a neutron and a proton to have the same mass. So the entire mass of the atom is due to the neutrons and protons. There's another little hint here if you want to look. Please look. So another hint to know that, at the top of the periodic table, if you zoom on in, you're going to see that they tell you the atomic mass number is above the atomic number. You should know the atomic number is the proton number. Okay, so this is the mass number, which we should know now is the protons and neutrons. So back to the problem. We have a mass of 20, which goes up top, and we have a proton number is 9. Of course, this is an isotope of fluorine because of the 9, as we just stated. So let's scroll our way down to an answer. The atomic number is 9. That is true. And the mass number is 20. So number 2 is the answer. Okay, and some basics you had to know for this. So number 2 is the answer for 33. All right, moving forward, number 34. A barium atom attains a stable electron configuration when it bonds. All right, well, barium is a metal. It's also a group 2 metal like we've been talking about with other problems. Barium has 2 valence electrons. Okay, so it loves to lose 2 electrons. Let's go to the periodic table to show you that. So barium is a group 2 alkaline earth metal. Okay, right here. Let's zoom in. And it loves to lose, like all alkaline earth metals, 2 electrons because it has 2 valence electrons in its outermost shell. So it loves to lose 2 electrons here, or its core electrons, and here it's its valence shell. Okay, so it loves to lose 2. So when it bonds, okay, especially ionically because it likes to lose 2 electrons, it needs to lose its 2 electrons to something that loves to gain them. So let's go back to the problem. All right, so we know that barium has 2 valence electrons. Okay, it's a group 2 element. It's a alkaline earth. Chlorine, okay, is a halogen who has 7. If you don't know that, let's go to the reference table here. And here's my chlorine. And chlorine has 7 valence electrons. Now, if you notice something, chlorine is all the way to the right. It's a non-metal. It's above the staircase. It's very small, very electronegative. Barium to the left is a very reactive metal. Okay, it's a big atom, loses electrons very easily. So this combination of metal to non-metal is going to be a scenario kind of like myself pulling a tug of war with my 3-year-old. I'm not only going to win the tug of war, I'm going to yank the rope away from my child and say, who's your daddy? Now, of course, I don't do that, but barium, I give him gloves. Barium is kind of like my child, okay, who holds onto the rope loosely, and I'm like the chlorine, the nonmetal, who is very attractive, very strong for electrons. We call it electronegativity. So there's going to be a transfer here. And now for barium to bond and become stable, it's going to want to lose 2 electrons, 1, 2, to become as stable as xenon, as we've mentioned before, and have that filled octet. Chlorine wants to gain just 1 because of 7 valence electrons and become as stable as argon. So the driving factor here in stability is having a noble gas configuration. Chlorine needs 1 more to have its stable octet. Barium needs to lose those 2 to have the stable octet like xenon. And that is the key to the question. So this is going to be an ionic compound that you're going to draw here, or at least try to figure out. So as we said, there's going to be a transfer. Barium needs to lose 2 to become stable. Chlorine needs 1. And because electronegativity differences are so great, this is 3.2 and this is 0.9. I got that from table S if you don't know that by heart. You'll see clearly that this chlorine is going to pull that electron and it's going to get reduced. And barium can't stay with 1 electron. It needs to lose 2. So the only way to do this, and you're right, you're going to need 2 chlorines. Another chlorine with 7 valence electrons is going to be necessary to pull the other electron away. And what you're going to get is you're going to get barium with no valence electrons left because it lost 2. Now because it lost 2 and got oxidized, losing electrons is oxidation, Leo, it became +2. And chlorine, okay, this chlorine had 7, but it gained 1 more to get that octet. And because it gained 1, it got reduced as -1. And we would need another chlorine. And again, I'm drawing a Lewis dot diagram here. You don't have to do that, but I'm showing you how this is all interrelated. Another chlorine has 7 valence, and it took the other one, okay, from the barium, and it also got reduced and now is -1. And notice the charge is electrically neutral. And essentially, you could have circumvented all of this, okay, by saying, well, barium, okay, is +2, and chlorine is -1, and you could have crisscrossed, okay, and reduced the lowest terms, okay, and you would have got 2 chlorines for 1 barium. So many ways to think about this. I over taught it, okay, but you should know all these concepts. So it needs 2 chlorine atoms to take both electrons so that it can have a stable noble gas configuration, and that's why things bond to become stable. So 34 is 2. Number 35.
35 states a student measures the mass and volume of a piece of aluminum. The measurements are 25.6 grams and 9.1 cubic centimeters. The student calculates the density of the aluminum. What's the percent error? All right, so density is nothing more than mass over volume. If you didn't know that, the top of table T actually gives you that. And there it is, table T. Density is mass over volume. So table T is again a place to look for equations. Okay, but that's not the crux of the problem here. The problem here is they want the percent error, okay, of the student's calculated density. So they want the percent error. So they calculate the density of aluminum. They want the percent error of the student's calculated density. Okay, so first of all, we're going to have to come up with the calculated density. So density is mass over volume, and the mass is 25.6 grams. The volume is 9.1. Now, cubic centimeters, if you remember, is centimeters cubed, okay? And that's a volume, length times width times height. So we're going to put that in our calculator. And when you put this in your calculator, grams over volume, you're going to get a value of 2.8 grams per centimeters cubed. Okay, now that is your measured value. Okay, and when we do a percent error, what we're going to do is we're going to take and compare our measured value with our accepted value. So we're going to need an accepted value. So where do we find that? Okay, well, table S gives us densities. Let's go find aluminum and find its density. Here is table S with its symbol, name, ionization energy, electronegativity, melting, boiling points, and now density. And we're going to go find, so this is the density column. Notice it's in grams per cubic centimeters. And we're going to find our aluminum. This is the line right here. And 2.70 is the known, okay, or is the accepted value from many experiments. So 2.7 grams per centimeters cubed is the accepted value. Okay, so now that we have the measured value that we calculated, that's the student experimental value, and we looked it up in a table, the accepted value or the theoretical value, now we can do our percent error. Now if you forget what the formula is, table T is your friend again. So percent error is the measured value, this is what we get from the experiment, minus the accepted value that we get somewhere, and we're comparing it to the accepted. So we're dividing by the accepted value and timesing by 100 to get a percentage. So we're going to use this formula given to us and plug in now. So when you take your measured value minus your accepted all over the accepted as outlined in table T for the percent error formula and times it by 100, you will get a 3.7 percent error. And we can round that to 4. And that's why choice 4 was the answer. So this is what I think they were talking about when they were making these B2 questions a little more tougher, a little more work here for this question. This was definitely a two-step problem. But 35 is 4 for that 4%, and you'd have to round to get that 4. Okay, now if you use the raw number here, 2.81, you'd get something like a 4.17 or 4.2, but still rounds closest to 4. Okay, so number 35 is 4. Number 36, given the balanced equation representing a reaction, what is the total mass of water? Okay, they want the grams of water. When 8 grams of hydrogen and 64 grams of oxygen, and here's a key, completely reacts completely with 64 grams of oxygen. That means both of these are limiting reagents. Well, the conservation of mass states, party people, that the total mass of the reactants have to equal the total mass of the products. Law of conservation of mass, if both of them completely react. So 64 plus 8, okay, last time I checked, okay, is going to give me that 72. All right, so this is a total mass of 72 on the reactant side. This has to be 72 on the product side. And that's why choice 4 is your answer. Now, you certainly, if you took a higher level chemistry class, could do the stoichiometry and convert your 8 grams of hydrogen to moles, right? So we got 8 grams of hydrogen, convert it to moles. We know that in 1 mole of hydrogen, we have 2 grams, and this would give me 4 moles. I would times it by the ratio. I'm going to get rid of hydrogen. And in the balance equation, there's 2 H's for every, okay, let's say we're doing water, right? 2 waters, that's a 1-to-1 relationship. So moles of hydrogen is moles of water, but our H2 cancels, and now we have moles of water. And if you want grams, going to get rid of your mole. 1 mole is how many grams of water? If you did a formula mass, it's 18 grams. And if you did 8 divided by 2, which is 4, times 2 divided by 2, which is essentially 1, and 4 times 18 is your 72 grams of water. So you could have done a stoichiometry problem, but for the rest of us, all they were looking for in this problem is something that comes up very, very frequently. If you've gone through all the June tests, especially the ones that I have done, this might be the 3rd or 4th one from 08 to 2012 that I've seen, where they just, all you're doing is massing the reactants and using that mass to get something in the products. In this case, it's the entire mass of the product since there's only one. It's a law of conservation of mass. If you didn't like this top explanation, that's okay. Mass of the reactants has to equal the mass of the products. So all we were doing was adding 2 numbers. Number 36 is 4. Number 37. Which compound contains both ionic and covalent bonds? If I've got ionic and covalent bonds, I'm looking for a polyatomic ion. Why? Well, if I take something called a nitrate ion, which is listed in the table, what the heck is that, table E, it's collectively -1, the whole thing. And why? Well, it's because nitrogen, when it bonds with oxygen, needed an electron to make it work. For instance, here's nitrogen, has 5 valence electrons. It's in table 15. It's 2-5, right? So it's got 5 available electrons. Okay, and we're going to put some oxygens around it. So I'm going to just kind of disrupt this organization here. I'm going to put 3 oxygens surrounding this N, and I'm going to put out the valence electrons 1, 2, 3, 4, and 5. You notice nitrogen needs to have 8 to be stable, so it's going to use the oxygen's electrons to help do that. Oxygen has 1, 2, 3, 4, 5, 6. It's 2-6, so it has 6 valence. This oxygen's happy. 1, 2, 3, 4, 5, 6. This oxygen is fine, but we're probably going to have to do here is add a double bond, okay, to make this work. So we're going to put this pair here, and now this oxygen feels like it has 8 by sharing, but this nitrogen has 2, 4, 6, right? 7 needs 1 more. We know that oxygen has 1, 2, 3, 4, 5, 6, and if you think with me for a second, nitrogen needs to feel like it has 8 to be stable, 2, 4, 6, 7. So what we're going to need is another electron from the environment to make this work. It may have got it from a metal. So this thing needed to gain 1. So my magenta one there represents 1 electron to make that work. Now, you didn't have to do all of this to answer the problem, but I'm showing you that between the nonmetals, they're sharing electrons. And it needed 1 to make this work. So this cluster of nonmetals is an ion because it needed an electron to make it work. But importantly enough, between the nonmetals, we're sharing electrons. So that is a covalent bond. So between the nonmetals, as you should already know, is covalent bonding. Why? Because they're forced to share. Why? Because they both have high electronegativities. Now this cluster is an ion because it needed an electron to make it work to become stable, for everyone to have its octet. So that's what this is. This is what the nitrate is. So in table E, you'll see a bunch of clusters of nonmetals that have charges. Now, where is the ionic bond if this is the covalent bond? Well, you're going to need something that is positive to attract it. Let's pretend that that electron, that magenta electron that I drew, okay, came from a sodium, that was its valence that migrated over. And if sodium lost that valence, or was just positive to begin with, okay, the attraction between the positive ion and negative ion is your ionic bond. So anytime you're looking for both ionic and covalent bonds, you're looking for a salt, something that's ionic, that has a polyatomic ion. And as if you haven't already guessed, sodium nitrate is the only thing here that has a polyatomic ion. Ammonia is NH3. And if you don't know what ammonia looks like, look at table K, I think, and it lists that there. It's for all the bases. Okay, it might be L. And methane, you should know from organic chemistry, is CH4. That's all covalent. Potassium chloride, you should know, is KCl. It's all ionic, metal, nonmetal. So the only place where we're going to have both an ionic and a covalent is when you have a polyatomic ion. So choice 3 is the answer for 37. Again, I probably overtaught it, but hey, I'm tall. Okay? Number 38. An iron bar at 325 Kelvin is placed in a sample of water. The iron bar gains energy from the water if the temperature of the water is what? All right, well, let's think about this. Heat always flows from hot to cold. So I've got a red iron bar, Fe. It's at 325 Kelvin. That's its temperature. Okay. Now, if it's gaining energy from the water, so it must be somewhere in contact with water. So here's our container, and let's draw in our water. We know that energy flows from hot to cold. Why? Because things that are hot are moving faster than are things that are moving slow, that are cold that are moving slower. So things that are slower get caught by things that are moving faster. So heat flows from hot to cold. So in order for the bar gaining energy from the water. Okay, in order for that to occur, the water has to be warmer, has to move faster, okay, for energy to flow. So I'm looking for a temperature that's greater than 325 Kelvin. Well, 65 and 45 Kelvin do not cut it. Okay, they're just too small. And if this was the temperature of the water, the iron bar is warmer and energy would flow from the iron bar to the water. So this cannot be. Now, your other choices are in Celsius, and the temperature of the bar is in Kelvin. So a couple different things you could do here. Okay, what I'm going to do is convert my Celsius to Kelvin. And I know that Kelvin equals Celsius plus 273. It's the same scale, the same size, except that Kelvin starts 273 degrees sooner. Now I'm getting this formula from table T. And there it is in all its glory. Kelvin plus, notice the Kelvin doesn't have a degree sign because it uses the Celsius scale. Kelvin and a Celsius degree are the same size. It's just that Kelvin has no negative numbers. It starts 273 degrees sooner. It's an absolute scale. So that's my formula. Okay, so using our formula, Kelvin equals Celsius plus 273. I'm going to plug in for my Celsius, 65, my choice 3, plus 273. Okay, gives me 338 Kelvin. All right. And 45 plus 273 gives me 318 Kelvin. So clearly 338 is a higher temperature than 325 Kelvin. So if the temperature of the water is warmer than the iron bar, energy would flow from the water to the bar, and the bar would gain energy. So the only choice that is warmer than 325 Kelvin is choice 3. 38 is choice 3. 39. 39 states which particle model diagram represents only one compound composed of elements X and Z. Well, if we're dealing with elements X and Z, then we're only dealing with, of course, we're dealing with a compound, sorry. So a compound's telling me that X and Y are bonded in some exact ratio. To be a compound, you have to have a distinct chemical formula that is fixed. So we're going to have some ratio of X and Z. Now, of course, a compound is two or more different elements chemically combined in a different ratio. Okay, so let's go look at the choices to see which ones we can eliminate. Okay, well, I'm going to eliminate choice 1. This is a mixture of just elements. This is not a compound. Compound has to be two or more different atoms chemically combined. These are diatomic elements. Here looks like a compound to me. There's my Z and there's my X bonded in a distinct ratio. Notice there is one X for two Z's. Okay, and that could be the chemical formula. So it looks like 3 is going to be my answer. Okay, and if I look at choice 2, it's just free atoms. So this is not a compound. Now, number 4, I have a compound, but I have several compounds with what? Different chemical formulas, along with different elements. So this is a mixture of 2 different elements and 3 different compounds. They just wanted one compound, which, by the way, is called one substance. So one compound, one chemical formula that's fixed. Okay, that's why 3 is the answer. So number, what was it? 39 is 3. Number 40. Okay, number 40, given the balanced equation representing this reaction, which statement explains why the energy term is written to the right of the arrow? Well, if the energy is written to the right of the arrow, this is the product side. This is the reactant side of the reaction. Okay? If you're producing copper 2 sulfide and you're also producing energy, that energy is free to leave, and we would say that it's exiting the reaction, and it's an exothermic reaction. Very important, you know that. So, which statement explains why the energy term is written? The compound is composed of 2 metals. By the way, it's not. It's a metal and a non-metal, right? S is above the staircase. The compound is composed of two nonmetals. Well, this is a metal. Copper, you should know, is a metal, but it's to the left of the staircase. Okay, so that makes no sense. 1 and 2 are poorly, terrible choices. If you pick them, you just don't understand much chemistry here. Okay, sorry if that was one of you guys. You should know who your metals and nonmetals are. Okay, 3, energy is absorbed. No. Okay, energy is released. Okay, now they added this section part to this as bonds form. Anytime you form bonds, energy is released. Okay, and actually energy is absorbed anytime you break bonds. But when you form copper sulfide, you also produce the energy. So they're after the idea that you knew this was exothermic, and exothermic means energy is exiting or being released. So that's what this question was about. There's nothing more to it. Energy on the product side means things are being released. Just like if you were to look at a redox reaction and put electrons in your half reaction on the product side, electrons are released. So if you were to write like for instance, we write the half reaction to this problem. I know it's not part of the problem, but think with me for 0 to +2. Copper, sulfur is -2. So that'd be a copper 0 becoming copper +2 and 2 electrons, so that both sides of the half reaction are neutral. We put the electrons on the product side because they're being released or they're being lost. And that's why we say losing electrons is oxidation. You're losing electrons. So for the same reasoning, so in any case, energy is being released. Number 40 is choice 4. Number 41, a 1 gram sample of which element will uniformly fill a closed 2-liter sample at STP? Okay, well, a lot of information here, but the key here is that uniformly fill a closed 2-liter container. So really what they're saying is which one is a gas. Only gases fill their containers uniformly, always. So at standard temperature and pressure, which is the phases that you learn about elements, which one's a gas? We have sulfur, tellurium, xenon, and antimony. Now xenon is going to be your answer and it's choice 4. And you should know who your gases are at the periodic table. Before we get that, you should know it's a gas. Why? Well, if you look at a container, solids do not uniformly fill a container. If you put a solid in, even if it's sand, you'd have to fill it all the way to the top, and that only if you have enough volume. But gases will always uniformly fill because they're flying around, and you only need one gas particle, okay, to actually fill a container. Okay, the funny line that I give is when I returned a helium tank years ago, it was just about empty of helium, but the guy says it filled, and I said, well, yeah. And I was thinking because if it just had one gas particle, that would bounce around and fill the container. Oops, it won't break the container like that. Okay, so it would bounce around in straight lines if it's an ideal gas and fill the container uniformly. Liquids and solids do not. Okay, so which one's a gas? Antimony, sulfur, tellurium, xenon. Now I know xenon's a gas, but let me show you who your gases are at STP. One way to think about your gases are at STP. You could look up their melting points, or boiling points I should say, in table S and realize, wow, something's got a real low boiling point. That means it's already boiled. That's one way to do it. But you should know this. You take this H to HE all the way down. It's kind of like a backwards L that fell down. I call it the LL rule. And you take this NOFCL, NOFCl, another smaller version of that backwards L that's on its side. Okay, if you pick it up this way, then that's all your gases. So hydrogen, helium, all your noble gases, including NOFCL, those are your gases at STP. You should know your two liquids. This is a non-metallic liquid, bromine. And of course, your metallic liquid at STP is mercury. Everything else is a solid. Okay, so there's only one gas there, and that was your xenon, I believe. That was in the problem. So the rest of these elements were solids. So the only one that was a gas is choice 4. Number 41 is 4. Number 42. Given the balanced equation representing this reaction, what is the total number of moles of O2 required for the complete combustion of 1.5 moles of C3H8, or better known as propane, prop, for 3 carbons, ane for single bonds? Now, we have 1.5 moles of your propane. how many moles of O2 is required? Well, my friends in chemistry, this is a stoichiometry problem. And the only stoichiometry problems that we see now in Regents Chemistry are mole to mole. Okay? And what you're using is the mole ratios, the balanced coefficients. Think with me for a second. We have one propane molecule for every 5 O2. So it's a 1 to 5 ratio. Now, a mole is really a how many number. So it's some kind of quantity. Just like a dozen is how many is a how many number as well. It's a word that describes a number. Okay, we use a dozen for the same reason we would use a mole, to take a large number and make it into a term that we can manage it, because a mole is a huge, huge number of particles. However, we're matching particles here, and there's 5 of these to 1 of these. So doesn't it make sense that all I have to do is times this by 5? Okay, now how I would teach this when I'm teaching stoichiometry, I would say, okay, 1.5 moles of my chemical given, in this case it's propane. I'm going to times it by the mole ratio. There's 1 propanes, C3H8, to 5 oxygens. And all I did, party people, was take the balanced equation and I put it right there. And in stoichiometry, what we're doing is we're canceling the compound given. We're given some information about one compound, and we're trying to answer for another. And lo and behold, by setting it up this way, I'm canceling out my propane to get to my oxygen. And as I already previously stated, aren't I really multiplying this by 5? And when you do so, you get 7.5 moles of O2. All right, and it's very, very simple. Now, for those that didn't like this dimensional analysis, I'm going to have to show you, because there are all different levels of students, there's something else you could have done. Now, the coefficients, if you like proportions, I'm not a big fan, but I'm trying to get people to pass the Regents who are not very good mathematically. So if you understood that, you can move on, but those that want another easier way, watch. This is a 1, and this is a 5. Put this on the denominator. Put this on the denominator. What does that give you? It gives you 1.5. Now let's just do it like this. It gives you, let's put it down here. It gives you 1.5. Yes, I can do this. 1.5 over 2, right, equals x over 5. Crisscross and solve for your x, you'll come up with 7.5. So you can build a proportion by putting the coefficients on the bottom and put the number they give you on top of the information you have. So this was for propane, and put your unknown for what they wanted. And it's another way to do it. These are mole-to-mole problems. Okay, sometimes you can just do it by just saying, like we just said, hey, it's a 1 to 5. Okay? So any case, be able to recognize these where they give you information about one compound and ask for another, not very difficult problems. That's hopefully now you see that. 42 is choice 4. 43. Okay, 43, a sample of a gas occupies a volume of 50 milliliters in a cylinder with a movable piston. The pressure of the sample is 0.9 atmospheres and the temperature is 298 Kelvin. What's the volume of the sample when you change it to STP? So this is a gas law problem. So let's go to the reference table, table S, to remind us what formula we need to use. So this is the combined gas law formula. PV over T equals PV over T. This is 1s and 2s. I like to think of this as the current scenario. This is the future. Okay, so let's use that for this problem. All right, so PV over T equals PV over T. This is my current scenario, and this is my future. So let's put this together. What's the current conditions? We have a volume of 50 milliliters, so I'm going to put 50 milliliters here. Okay. The pressure of the sample is 0.9 atmospheres, so 0.9 atm. The temperature is 298. Kelvin. It was nice of them to put it in Kelvin for us. If it wasn't in Kelvin, it'd have to be converted to Kelvin. All of our relationships of pressure with temperature, volume with temperature, is only directly related if you're at a Kelvin temperature. Okay, so that's our current scenario. Now, what's our future? Our future is that we're going to make it at STP. So what's the volume at STP? Well, the volume is something we're solving for, but what's the pressure and temperature at STP? A lot of people with this question say, Mr. Grodsky, they didn't give me enough information. No, no, no. By saying STP, they're saying standard temperature and pressure, and we've got a table, the first table, table A, that gives that to us. And there is table A in up close and personal, and standard pressure is 101.3 kilopascals or 1 atmosphere. Standard temperature is 273 Kelvin or 0 degrees Celsius. We're going to use the units that are the similar in the problem. Of course, temperature is always going to be Kelvin, okay, in a gas law problem. So I'm not going to use 101.3 kilopascals because those weren't the units we were given. We have to have them cancel. So we're going to use this. We have to use the same units here as the question was started with. So there's my volume, my pressure at STP, standard temperature and pressure, is going to be 1 atmosphere, as we see from our reference table, and our standard temperature is 273 Kelvin. So just plug that in. Now, a part 2 question, sometimes they just give you entire correct answer for this. Now we're going to solve for V to come up with a number. Okay, so let's do that. Let's make some more room for ourselves as I white out on the problem. Okay, and let's make sure I make it smaller. So I'm going to solve for this algebraically. I'm going to put V by itself. Now, for those weak in your algebra, what I'm going to do is multiply this side by 273 over 1 ATM. And what I do to one side of an equation, okay, oops, I do to another. Oops, let me get back. Sorry about that. So what I do to one side of an equation, I do to another. So this would be 273 over 1 ATM. This is kelvins, of course. And what's going to happen is these guys would cancel and left with V. Now, for those that have been doing this long enough, you know that another way to do this is put whatever's on top on the bottom, right? What's on the bottom goes on top. It's the same thing. So what you're left with, either way, is you're left with, okay, 0.9 atmospheres. That's from the what? The current scenario, 50 milliliters. Okay, we're going to have 273 Kelvin. And on the bottom, we're going to have 1 ATM with the already 298 that's there. And now we just have to solve. Now, interesting enough, maybe not that interesting, okay, the atmospheres cancel, the kelvins cancel, and you're going to left with milliliters, which is a volume unit. So you got to put this in your calculator. So I'd go 0.9 times 50 times 273, divide by the product of these two numbers. Now, this is a 1 here. So that means, so it's divided by 298, but this wasn't a 1 here. I would do parentheses in my calculator. So in any case, let's do that math in our calculator now. Okay, when I do that, I get 41.2, which will round to two significant figures to 41. And that's why choice 1's the answer. Now, one thing you should always do with these problems is see if your answer makes sense. Remember, we initially had 0.9 atmospheres, 50 milliliters at 298 Kelvin. Our temperature dropped a little bit, okay, and our pressure increased a little bit. So essentially, our 50 milliliters shouldn't change all that significantly. And of course, 41 is close to 50, so this makes our number make sense. Okay, so that's how you should look at that. In any case, okay, number 43, okay, is 1. Number 44. Number 44 is a colligative property question. As we've talked about previously, thumbs up and thumbs down. I think I'm missing a finger, but the boiling point is going to be elevated. the freezing point is going to be depressed when you add solute particles into water. It's called a colligative property. The properties of the solution are going to be higher in its boiling point and lower in its freezing point compared to the pure solvent, the water. And that's because the solvent particles are getting in the way, okay? Getting in the way of the water. So as you add potassium chloride, it's harder for it to boil, so it needs a higher temperature. It's harder for it to freeze, so you need a lower temperature to slow them down. So I'm looking for the greatest amount of solute particles. The more stuff that I put in the way of my water, the harder it is for my water to freeze. And that's why when you throw salt on ice, you get more melting because it lowers the freezing point, which means the air temperature now is warmer. So I'm looking for the greatest amount of solute particles dissolved. So I've got 10 grams in 100. I've got 20 grams of Ki in 200. Now, isn't that the same thing? 10 in 100, 20 in 200, right? Remember when we did table G and we had anything that was twice as much water? Table G is based on 100 grams of water. Well, if you had 200 grams of water, you double it. Well, this is 200 grams of water. Compared to 100, it's the same thing as a 10 to 1. So choice 1 and choice 2 are really the same quantities. Choice 3, 30 grams in 100. That's pretty high. And then 40 grams in 200 is really 20 grams in 100. So the one with the greatest amount per 100, and that's how I would think about it, because 20 in 200 is the same thing as 10 in 100. So this is really 10 in 100. This is 10 in 100, so 1 and 2 are the same. 30 in 100, that's definitely a higher ratio of solute particles. And this is 40 in 200, but when we change it to 100, it's really 20 in 100. So choice 3 is the best answer with the greatest amount of solute particles. And all I did was a little bit of ratio there. Okay, number 45. Which 1 mole sample has the least entropy? Entropy is chaos. It's disorder. So I'm looking for something that is random, disorder, has tremendous energy. So temperature gets my eye first. And I can see something with the greatest amount of temperature, okay, is going to have a lot of movement. The next thing that gets my eye is the phases. Gases are traveling in the air hundreds of miles an hour. Liquids are moving at a pretty good clip, but they're locked to each other in a certain volume, and solids are fixed in one position and vibrate in their fixed position. So gases are more disordered. So I'm looking for the greatest temperature, and a gas would give me the greatest amount of disorder, choice 4. A solid with the, good thing I read it carefully. A solid, the answer is not 4. Okay, because they're looking for the least entropy, and I answered it for the greatest amount of entropy. Got to be careful like I wasn't. Okay, so they're looking for the least amount of entropy. And I guess a good way to do that is to underline what they're asking for, to remind yourself, because I almost got this wrong here because I wasn't paying attention. So the solid, because the solids are in a fixed geometric, regular repeating geometric pattern that vibrate in their fixed positions, okay, they have the least amount of disorder. And if you make them have a lower temperature, they're going to vibrate even less. So the lower the temperature and the less freedom of the phase, we're going to get choice 1 as our answer. Okay, least amount of disorder is your solid under the coldest conditions. And the greatest amount of entropy, which I was trying to answer, okay, would be the gas, the highest temperature, greatest movement. 45 is 1. 46, at 20 degrees Celsius, a 1.2 gram sample of magnesium ribbon, that just means a thin piece of magnesium, and we had this in lab if you're with me, reacts rapidly with 10 milliliters of 1.0 molar HCl, makes it hydrogen gas that we actually did in a UDiometer tube. We measured the molar volume. Remember that lab a while back? Maybe, maybe didn't. Doesn't matter. Which changing conditions would have caused a reaction to proceed more slowly? So this is a rate of reaction problem. Okay, so we want to make this more slowly. Okay, so we're looking for some factor that's going to make the reaction react slower. Well, increasing the temperature is going to make the reaction go faster because it's going to create more effective collisions, because Higher temperature means more motion, more collisions. We're looking for less collisions. Decreasing the concentration of HCl to 0.1 is going to be our winner here, because this one's going to lower the number of dancers on a dance floor with the same volume, so the number of collisions on the dance floor are less. The dance floor is the reaction container. So if you got less HCl, there's less of these to collide with the magnesium, so the reaction goes down. So 46 is 2. Let's look at the other questions. Use powdered magnesium. Well, that's going to expose more atoms, increasing the surface area. The reaction rate's going to be much faster. They want to go down slower. And then, of course, use 2.4 grams of magnesium ribbon. They're just increasing the amount of magnesium. So that would also increase the rate of reaction, possibly by Le Chatelier's principle. So 46 is choice 2. That's the only factor that would decrease the rate of reaction. 47. Okay, which general formula, and these general formulas, my friends, okay, usually come from table Q, but it doesn't really matter to saying which one fits this. So let's look at this for a second. 1, 2, 3, 4. 4 carbons, so that's C4. How many H's? 3 plus 2 is 5, plus 1 is 6, so H6. Now if I counted correctly, I have 4 H's and I have 4 carbons and 6 hydrogens in this hydrocarbon. So which formula? Well, I can cross off number 1 because this says CnH2n, meaning the same number of carbons will always equal the hydrogens. Well, that's not the case. They're different. I can cross off number 2 because number 2, which by the way is the alkenes listed in table Q, is double the amount of H's compared to carbon. Well, if this was fitting, if this was correct, this would be C4H8. So that's not going to work. I think 3 might be our answer here. Double the amount of carbons, that would make it an 8, right? 2n, so 2 times 4 is 8. Then subtract 2, and that would give me my 6 for my H's. So this is the formula that fits that hydrocarbon, so choice 3 is the answer. If you were to draw this, you would see that this was an alkyne, and you learned in table Q that these are alkynes. So you could have done it this way. CH3, I'm just drawing the structural formula, CH2, dashes represent the hydrogens, right? CH2, CH2, CH3. Now I have a C hanging out by itself, and then a CH. Well, we know carbon has to have 4 bonds. This carbon only has 2. This carbon only has 2. So the only thing I can do here is add another bond, maybe. And when I do that, oh, this carbon has 3. This carbon has 3. Still not going to work. It needs another bond. And that is now works. Now this carbon has 4 bonds. This carbon has 4 bonds. Every carbon must have 4 bonds in your drawing. And by the way, a triple bonded hydrocarbon is an alkyne. Table Q shows you that. And there is my table Q, and look at that. There's my alkyne, ethyne, and there's the formula that fits because there's a triple bond. Okay? Number 48, which compound dissolves in water to form an aqueous solution that can conduct electrical current? Who is an electrolyte? My friends in chemistry, acids, bases, and salts, which are ionic, are your electrolyte. They break apart into free ions. This is not a salt or an acid or a base. This is a molecular compound. This is also a molecular compound. It's not a base. It's an alcohol. Okay? This is a molecular compound. It does not break apart into ions. And the Cu group is an organic acid. So this is your answer. When in doubt, pick the Cu group. Okay, organic acids dissociate into their conjugate bases, which have ions. So acids break apart into free ions, and when you have free ions, you can conduct in solution. Acids produce ions, bases produce ions, and ionic compounds break apart, like sodium chloride breaks apart into free ions. Choice 3 is your answer. Number 49 states, given the equation representing a reaction at equilibrium, the H plus acceptor for the forward reaction is, this is that other reaction. Well, who's accepting the H in the forward? This is the forward, or this is the current scenario, this is the future. So if I look forward, NH3 in the future is NH4 plus. How did that happen? How does NH3 go to NH4 plus? How does this happen? It does so because there must have been an acceptance of a proton. And this guy must have one less, and H2O becomes OH minus because it lost a proton. So the one who accepted has to be NH3, and that's why we consider NH3 a base, because in water it will produce indirectly a hydroxide ion. It's not an Arrhenius base because it has to accept an H to act like a base, and that is the other definition, which they don't mention by name, but I will if I say it softly. Bronsted-Lowry, okay? But they say other. So the water is acting as an acid because it is donating an H plus, and NH3 is acting as a base. They're not going for that. But look at the reaction. As he going left to right, NH4 plus has one more than NH3. The only way that could happen is this guy had to accept an H. 49 is 2. Number 50. Number 50 states an original sample of K40 has a mass of 25 grams. After a certain amount of time, many years, that how many grams of the original sample remains unchanged. What is the half-life of K40? Now, people know, hey, I know half-lives are in Table N, but you won't find K40 in Table N. They want you to be able to solve for it. So we're going to have to do a half-life problem. Now, I do half-life problems with a zero line. 0 half-lives, 0 time, okay, and 100% of my sample. Now, in this case, the 100% of my sample, okay, was 25 grams. Now, what's going to happen? Well, over time, it's going to decay to 3.125 grams. Let's go find how many halvings occur to get the 3.125 grams. So let's do that. So in the first half-life, 12.5 divided in half is what? 12.5. In the second half-life, I divide 12.5 by 2 and I get 6.25. And in the third halving, dividing 6.2 in half, you guessed it, I get 3.125, which by the way is what they said up here, okay, that it decays to. So I realized 3 halvings have occurred, 3 half-lives. The total time is from 0 to the 3 halving is 3.9 times 10 to the 9 years. Okay, well that's a total time, but 3 halvings have occurred. So what's the time for each half-life? I divide by 3. Okay, and 3.9 divide by 3 gives me 1.3 times 10 to the 9. And that's why choice 1 is the answer. 50 is choice 1. Nice little half-life problem to end off question number 50. You should see eventually a link once I'm done with it for the free response section of this test. Hope you enjoyed. Hope this helped. Rock on.